So my name is Ravin Bhatt, one of the organizers, and chairing the afternoon session. We have 4 talks, 2 before tea break and 2 after. And the first one is by D Sarma of Insitute of Science, who is going to tell us about nickel sulfide, the curious case of nickel sulfide.
Thanks, Ravin. I need to lower this. Let me start by thanking the organizers, Krish, Ravin, and all others for inviting me to share some of our recent results in this very important conference, which is dedicated to Professor T.V. Ramakrishnan. Before I get started, I should like to point out that the work that I'm going to present is essentially done by this PhD student who's jointly supervised by my colleague Indra Dasgupta at Indian Association for Cultivation Science and myself. It really gives me great pleasure to have this opportunity to present this result in TV's 70th birthday. TV has been an inspiration and a teacher. We'll talk more about it later in the evening. I don't want to preempt myself, but I would simply dedicate this talk to TVR. I've given a slightly provocative title, deliberately, The Curious Case of Nickel Sulfide. Let me define exactly what is so curious about the nickel sulfide case. And the essential, if I have to give a one-line summary of the curiosity of nickel sulfide, it is the fact that we cannot make out whether it is a metal or an insulator, which is somewhat surprising because most of the time it's rather easy to figure out if something is a metal or something is an insulator. That's the simplest thing that we all thought right from our childhood, from the school days. We have been taught how to distinguish a metal from an insulator, and that definition has been added by many other properties and measurements that distinguish very clearly between what should be a metal and what is an insulator. But as I go along, I'll try to point out why the confusion comes and what is our story about that particular issue. Let me give a brief introduction to the case of nickel sulfide first. So the crystal structure, and there's a very spectacular phase transition in this. To talk about the crystal structure, it's a hexagonal structure where you have this AB plane of nickel alternating with sulfur planes and nickel planes and sulfur planes and nickel planes. The basic idea, the electronic and magnetic properties are going to be determined by this octahedral coordination around the nickel of sulfur. So this NiS6 octahedra. And these octahedra are connected along the AB plane by phase sharing between the 2 nickels. And along the C-axis of the hexagonal, that is, they're sharing the edge. So it's basically phase shared in nickel S6 octahedra in the AB plane, and the edge shared nickel S6 octahedra along the C-axis that define completely the crystal structure. But I've also mentioned about the phase transition. It turns out that it has a very spectacular phase transition. The structure type is known as the nickel arsenide structure type. This first order phase transition is at about 263 Kelvin. It is more or less understood and agreed upon by everybody that the high temperature phase is a paramagnetic state and the low temperature state is an antiferromagnetic state. So there is, experimentally at least, so there is not a very large amount of disagreement about the magnetic structure, though we do believe that there may be some twists and turns even in the magnetic structure at low temperature, but that will not be the subject matter of today's talk. So it is a very strong first order transition at 263 Kelvin. And there's a small change in the volume changes by about 2% across the transition. The volume is larger at the low temperature.
Same temperature as the crystal transition?
There is no crystal structure transition. There is change in the lattice parameters. The volume changes. The crystal structure remains the same. And they coincide, of course, the magnetic, it's a first order transition, as you'll see in a moment. And there's a very catastrophic change in the transport property also that I'll be showing you. So the magnetic structure is also quite an interesting one. It turns out that it's all the nickel ions, it's nickel 2 plus all of them, are ferromagnetically coupled along the AB plane. And these AB plane ferromagnetically coupled layers alternate antiferromagnetically along the C-axis, and that makes the overall antiferromagnetic structure of this material. And this is the resistivity. The resistivity of nickel sulfide. You'll notice that I've put some selenium also. In a moment I'll explain why. Because you can systematically affect the this transition, phase transition by changing the selenium content. But if you look at nickel sulfide, x equal to 0, what it shows is that there's this resistivity, the high temperature resistivity, which I said there's not much controversy about it. It's a polyparamagnetic metallic system, a very good metallic system. It has this very strong first order transition, and then it gets into this state. And let me first illustrate how we can affect this phase transition by changing the selenium content, and that's shown over here. If I put 4% selenium, or 6%, or 11%, I keep pushing the transition temperature down. If I go beyond 14% or so, 15% and 17% ends up being a very good metal, polyparamagnetic metal. That's the, are you talking about this jump, or are you talking about this jump? That jump, that's, okay, that's the experimentalist problem. Since it's a phase transition of the first order kind, the volume changes and it develops micro cracks. Okay, so it's just an artifact, so let's not worry about that right now. Okay, so so you can push down the transition temperature, keeping the lattice the same, the structure exactly the same, and in fact you can push it all the way to the metallic state, and that would be useful for some of the results I'll be presenting later, because that provides a very good reference material down to the lowest temperature, what the metal would be if this state persisted down here. Since we cannot make that state persist here, we get preempted by this first order transition. If I want to understand this state compared to what this state would be, I would like to study this system, because that I can take to the lowest temperature and compare that with that one and figure out what's happening. Now, immediately you'll see that there's some very surprising thing. Of course, these metallic states are very good metals. I mean, in the order of 10 to the power minus 5, these are polycrystalline samples, and getting a 10 to the power minus 5 ohm centimeter resistivity is as good a metal as you can get for inorganic compounds of this kind. But if you look at the resistivity, it's in the order of 10 to the power minus 2 ohm centimeter. Depending on how well or how badly you make, and there's single crystal data also available, it's in the order of 10 to the power minus 3, 10 to the power minus 2 ohm centimeter. Now that's a very bad, because normally I should be able to make out if something is metal or something is insulated, but just looking at the low temperature value of the resistivity or conductivity. But it turns out to be in a very awkward regime of values in the order of 1 million centimeter, which is neither here nor there, and it doesn't help me to understand whether it's metal or insulated. Of course, the next thing that you know is to look at the temperature coefficient of resistivity, because we all know that don't look at only the resistivity value, but look at the temperature coefficient of resistivity, and you are looking at the temperature coefficient of resistivity. Your guess is as good as mine. You can have 0, plus, minus, whatever you want, but it's essentially 0. And that's between 4 Kelvin and 260 odd Kelvin, which would say that if it is an insulator, then the measure of the gap is much less than 4 Kelvin, which is very, very, very soft milli-electron volt gap, which is very surprising, because any such gap would be completely wiped out by any amount of disorder, and you would have a gap, non-gapped material. And if it is a metal, then also it's very surprising, because it has such a large resistivity, and also there is no effect of the usual effects that we would expect in a metal, making the conductivity or the resistivity come down as I lower the temperature. So there seems to be some kind of scattering that's temperature independent, determining if it is to be a metal. So these values, this transition, it's not quite monotonic that you can see already, right? But remember, there's a larger gap. I've not plotted it and not looked at it really. So I do not know, because you have to be careful about the resistivity absolute value in a polycrystalline sample, because you have grain boundary contributions, indeterminate amount. Okay, so that is a bit of a difficult thing. Okay, so then if resistivity doesn't work, and as I said that resistivity doesn't work for, summarize the two main problems of trying to deduce whether it's a metal or not from the absolute value of the resistivity as well as from the temperature coefficient of the resistivity. So one can go and look at Hall coefficient, because that can tell me what is the carrier concentration, and that's of course what one did. And here's the data for the Hall carrier concentration, Hall coefficient. It's plotted over 1 over T. So if you're looking at the low temperature, most of the time I'll be talking about low temperature because there's not so much of controversy, or there's more or less complete agreement about the high temperature phase. So you have to look at this part, the part up there. In the high temperature phase, which is on this side, you can see that the RH drops down by approximately a factor 40, showing that there's a lot more charge carriers, and that we're not interested in. And also the charge carrier concentration extracted from these numbers are given over here, but there should have been only one plot if I'm talking about nickel sulfide. The reason that you have so many plots is because there are other complications that come in. One of the complications that comes in is the fact that nickel sulfide doesn't form only as nickel sulfide, but if you notice what's written over here, it says nickel 1 minus X sulfur 1. So there are nickel vacancies. And these nickel vacancies are written over here. So these are for different nickel vacancies, right? So one would say, well, if I convert it into carrier density, it's in the order of 10 to the power 20, 10 to the power 21 per cc, which is not such a small number. This number is pretty good and would be some kind of a metal, not an insulator. But then, immediately, somebody did what Vijay was asking me with this data to plot it as a function of the X, the concentration. Or rather, the carrier concentration as a function of X. And when they linearly extrapolated it to zero concentration, they found that the carrier concentration, zero vacancy concentration, they found that the carrier concentration also gets very close to zero. So this has been both the excitement and bane of nickel sulfide, that every 5 years or 10 years, there have been one group of other that jumped in to say it's insulator, and if somebody said insulator, 5 or 10 years later, somebody said it's metal, insulator, it was going on for a long time. And it will go on for some more time even after this talk, I'm sure. But let's go on. So there's this basic observations from the whole data I've shown. And the kind of summary of this kind of transport data would be that we have bad resistivity. So it could be an insulator. Well, if that's an insulator, because of temperature coefficient of resistivity is so close to zero, it couldn't be an insulator, so maybe it's a metal. But if it's a metal, then I have the charge carrier density, charge carrier concentration dropping by a factor of 40 across the high temperature to the low temperature. That implies it must be an insulator. But then I'm left with still 10 to the power 20, 10 to the power 21 per cc carrier concentration, so it should be a metal. But then if I extrapolate this charge carrier concentration as a function of stoichiometry, or the nickel vacancy concentration, I come to a number that's very small at the end, so it's an insulator. So this went on, and then of course one would think that we should be able to get the idea then from spectroscopic data. And there are two kinds of spectroscopy that we can do. One is the optical conductivity, and that was of course done. The optical conductivity is shown over here. This is a high temperature phase that I keep telling you I'll not talk about, and I go on saying I'll not talk about, and I'm mentioning I'll not talk about it. That's the boring metal. So this is the low temperature phase for a certain concentration of nickel vacancy. And those who believe that it's an insulator say, aha, look how the spectral rate drops down very drastically, creating a clear gap of the measure of about 0.3 electron volt. And if you really want, the gap is there about 0.18 electron volt. And they emphasize this dip. Those who like it to be a metal, they say, aha, but then don't forget you're getting this slide going up at the lowest frequency. Yes, please.
The Epson rule doesn't look like it works as I go from one phase to the other.
No, it doesn't, and I'll show you why. The volume of the formation, these two are not related. First order transition, it's completely different electronic structure. The form surface is extraordinarily different. Extraordinarily different.
Is there any indication of local movement in nickel?
In the low temperature phase, very large.
In 1.5
Bohr magneton per nickel.
experiment.
Deduced to be from neutron diffraction data, very old neutron diffraction data. We are in fact thinking of revisiting neutron, and we are proposing neutron measurements for certain specific reasons. It's a very, it's a local moment. That doesn't have to be an insulator. Yeah, it's a large moment entity. Okay? So there's this small amount of Drude peak which is consistent with this 10 to the power 20, 10 to the power 21 per cc. those who don't like that, they say, well, that's because it's doped by the vacancy. So it goes on and on. So one said that, okay, I mean, if that is not the case, let's go to the photo emission, because photo emission at least will directly look at the density of states or the spectral weight at the Fermi energy and will tell me whether at the Fermi energy there is any spectral weight or not. If it is there, and if it is sizable, it must be a metal. If it is not there, then it must be an insulator. It's a very, very simple-minded approach and very effective. And that's what Professor Fujimori did. And his results are shown over here. What he showed is that these are the nickel sulfide, room temperature 300 Kelvin, 190 Kelvin. These two are below the transition temperature. These are room temperature. So there is a phase transition across that. Not all of you are trained very well as spectroscopists, so I have to guide you through this a little bit. There is a shift. Basically what you're looking at is that this is the Fermi energy. So eventually you are interested in looking at the intensity, spectral intensity at that point. And we'll go and look at that. But before that, the observation that was made that, look, as we lower the temperature, this main peak position shifts to the left. Left implies higher binding energy. So the nickel states are getting pulled down, and if it is shifting down, it can effectively open up a gap here. So it is sort of an indicative, suggesting that there is a gap here by looking at the peak, high intensity peak, somewhat down in energy, and there's some little bit of shifts there. And then of course Fujimori went and looked at very close to the Fermi energy too, and the data are shown over here. This is the dots are the experimental data. You can see in the previous view graph you had 2.5 electron volt, about 3 electron volt spread, but now you have a spread of about only 0.45 electron volt, 450 milli electron volt. So we're really stretching out so that we can see very carefully what's going on right at the Fermi energy. And this is the experimental data at 300 Kelvin. And that 300 Kelvin data, since it's a metal, we should be able to assume a certain kind of spectral density, take into account the Fermi Dirac statistics, convolute it with our resolution function, which you know fairly well, and compare. And that's what they did. They said that, look, if I have I call it the density of states, let's say density of single particle excitation states, if it looks like that at t equal to 0 and it continues, it can be me. Okay. Was it something that I was doing? Huh? I couldn't answer the nature of that question. Did it? No, I lowered it down deliberately because normally if I keep it up there, the case comes down. So, okay, so, and in the unoccupied part, it's assumed to be continuing like that because you need to know that in order to put in the Fermi Dirac factor. And once they do that, then this solid line that you see is not a guide to the eye, but actually simulated, assuming that the density of states is running like that, cut off, and then you bring in the temperature, so on and so forth. And that's a pretty good description of it. Wonderful. Now then they went to the 190 Kelvin or 190 Kelvin, and this is the experimental data. The solid line is still the solid line that you had here. And you can see that there is a slight shift. This data, the actual experimental data at low temperature, is shifted to the left with respect to the room temperature density of states. And that, in order to estimate exactly how much that gap is, what we was to shift this solid line rigidly to the left by a certain amount. Okay, and then they shifted it by 10 millivolt, and you see how beautifully it then describes. And they came to the conclusion, so it has a 10 millivolt gap. Of course, this is not quite consistent with the optical conductivity data that you saw. There's no 10 millivolt evidence. There's a 0.18 millivolt, there's a 0.18 electron volt, there's a 0.3 electron volt, but there's no 10 millivolts. But this is the conclusion that it's an antiferromagnetic insulator with an extraordinarily narrow gap of 10 millivolts. Okay. And that was in the year of 1994. So about 4 years later or 5 years later, by the theorem that I told you that every 5 years somebody comes along, so we came along and looked at it with somewhat higher resolution than was available to Professor Fujimori at that time. And what we found is shown over here, first of all. So I'm showing you 3 different spectra. And now, mind you, this entire stretch is 80 millivolts, not 450 millivolts that Fujimori's data was. It's 80 millivolts, the whole thing. And there's a 2 millivolt drawn for you to to tell you that we can resolve everything down to about 1 millivolt or so. The data we have, this is a silver data, which has a solid line through it. This is the nickel sulfide data, and this is the nickel sulfide doped with selenium in such a way that it's totally a metal at lowest temperature. And all of them completely coincide over here with the Fermi energy. Okay? So basically this one, which is between the well-known metal silver and well-known metal here of the same crystal structure, suggests that there is no large gap. If there would be a gap of 2 millivolts, we'll be able to see that very clearly. And there is no gap. If there is a gap, that has to be lower than 2 millivolts, which would be consistent with the fact that the temperature coefficient of resistivity does not give us an exponential upturn down to 4 Kelvin. We looked at it a bit more carefully. What we did, these are the 4 samples. These two show the transition. This is very close to the phase boundary with respect to the composition that would have still the first order transition. These two just across, and these two are always metallic, and they don't. These are at high temperature, room temperature, very highly expanded range, and we can see that if I look at the gross part, they all look the same, and even if I expand exactly at the Fermi energy, they look exactly overlapping with each other. Absolutely no distinction between them. These two will remain in the same state as here as I lower the temperature, so that I have a good reference at the low temperature, and I don't have to do the jugglery of taking into account Fermi direct statistics distribution separately in hand. And those immediately find that at low temperature, these two that show a transition separate out from those which don't in this energy range, but not in this energy range. Showing that there is something happening across the transition. It's not nothing is happening. Something is happening, but what is happening, that is what we try to understand. Before I do that, I would like to show you the point that it actually looks like a metal, not only by the fact that we don't see a gap opening up, but we can also probe how the spectral weight is above the Fermi energy in photo emission with great accuracy and tremendous amount of resolution, because what we can do is systematically change the temperature of the sample. As we change the sample temperature, I'll be populating across the Fermi energy if it is a metallic state, or insulator depending on the gap size, and I'll be able to block out electrons from above the Fermi energy in the process, and I'll be able to map out what exactly it looks like above the Fermi energy. And if I do that, and there's silver, just to tune your mind, what we see is exactly the kind of depletion in the occupied state and building up in the unoccupied state, this part being exactly equal to this part as it should be. It's nothing but the Fermi direct distribution. So keep that in mind, and then when you look at the nickel sulfide case, it's shown over here, forget this line for a moment. If you look at the rest of them are nickel sulfide, all below the transition temperature from 165 to 25 Kelvin, and you can see that all of them go to the same point exactly the way it happens. There's this depletion of states and states that are building up, telling me that there's actually continuous spectral weight right across both in the single particle and normally at equal to 0, what will be the particle addition spectral part. What this line is that I told you to forget about is actually the room temperature spectrum, and immediately you can see that actually what happens between the room temperature and the low temperature is a spectral weight decrease at the Fermi energy and not a gap. And that we have marked over here how much that drop is. So with so much of experiment, all kinds of experiments that are possible being available, one would think that nickel sulfide is really an overdetermined case. And one should be able to understand what's going on there. And one should be able to understand by going over maybe to first principles calculation to the extent one can believe that. And that was of course tried. And it was tried and was shown that one group find that it's metallic solution in 1991, and about 8 years later they found it to be insulating ground state, both by density functional theory. So there also there was no agreement. So one group thought that it's metal, the other group thought it to be an insulator. So, sure.
The whole idea here is to make it look like one electron.
Yeah.
There are many electrons here. So
absolutely. Absolutely. So up to this point, there was no attempt to say whether it's one electron or many electron, because we were looking at experiments. Right? So after that, now on, I'm going to say that what one electron picture has to say, an effective one electron picture. The criticism that we provided is of course well understood by every child in the subject, and this is a standard criticism, and anybody can do that criticism. And we don't ask that. So what my purpose would be is to show what the density functional theory can tell us, and beyond that is not my competence, and I'd be very happy with people that are here who could take it beyond. Because there are many ways of reducing 10 to about 24 electrons down to 1 or 2 or 10, depends on what you want to look at. Yes, please.
Iron antimonite, the copper insulator, for example, which is supposed to be insulators, but never really insulating. They are just exactly like what you're showing.
Absolutely. I didn't want to say this. And we're trying to understand that aspect. This has something very much to do with those. And I'm going to bring out some points which are unique, and I believe those are true there too. Okay? But we are exactly at that point. We have not started looking at it, but we have understood that there is a connection there, because I came across in some talk, and I realized that, oh my God, this is exactly the kind of stuff that we are seeing, and so we have to understand a bit more of this. Yes? Thermopower, yes. Thermopower.
You say you still got the termite.
Yes, thermopower. Thermopower is again is a really crazy beast, and we're looking at the thermopower too, in collaboration with a group in COM. And what happens is, of course, the high temperature phase that I'll not be talking about, but in the below, it's very high, sort of insulator-like. Go down in temperature, it begins to come down and becomes very small at the low temperature. And this is a transition nobody has realized. It's transition across over we do not know, but it's really remarkable. And this result, I'm actually preempting something that it's collaboratively we're looking at. So it's something that not of many and near archive this data. So please.
So if there's no problem on the photon emission, such a poor metal/insulator charging it.
No. We have had the strontium titanate recent photo emission, Marcello's. Here definitely there's absolutely no problem. We can get away with model, we can get away with reasonable insulating systems, and charging doesn't show up, happens. If charging did matter, it would only shift the system to the lower binding, to higher binding energy, opening up a gap. So it would go against the kind of conclusion that the final conclusion that I gave and the final conclusion that will come up. Very strong. Yeah, but it's not the Kondo model, but I'll show you some aspects in the electronic structure which seem to reflect in also this iron antimonide and FU such systems. Okay, so fine. So I'll not tell you the computational details, that's of no interest, but essentially that I'm going to point out all the limitations of what I'm going to say. We change the value of U, we look at what has lower energy, and that would indicate what the first order transition would be. So this phase diagram is a pseudo phase diagram in the sense that we do not have at will the possibility of changing U, but I'm showing you what would happen if we could change U, the Coulomb interaction strength. And this is the band gap. The band gap is plotted over here. So you can see that there's a metal insulator transition. Everything on that side it must be insulated, everything on this side must be metal. And there's a magnetic moment, and that implies that everything on that side is magnetic, everything on this side is non-magnetic. And the magnetism that's lowest energy in our case is an antiferromagnetic metal. Antiferromagnet. So immediately you can see that means what I have is a non-magnetic metallic slice here, then I have an antiferromagnetic metallic slice here, and then I have an antiferromagnetic insulating slice beyond. So these are the three segments that come about, and let's look at the electronic structure of each of these types. So this is the LD, without any U value, the paramagnetic metallic state, and the very complex Fermi surface that I've shown over here. We can increase the U value largely by 2.4 electron volt, keeping the non-magnetic state, and you'd see that hardly anything has happened. There's absolutely no change that really happens. Okay, so what we are showing is that this is the one that I just now showed you. So this one belongs to this non-magnetic metallic state. If I increase the U value that I showed you already to 2.4, I get into that part, that is the metallic solution, but I have shown it as a dashed line because this is not the lowest energy state. The lowest energy state electronic structure looks completely different, and that's shown over here. And you can see what the firm surface looks like, and that dominates this antiferromagnetic metallic state. That's why this is antiferromagnetic metal. This would have been a paramagnetic metal here, but across this boundary, the antiferromagnetic metal becomes more stable and non-magnetic metal becomes more stable on this side. So there's a first order transition across here. And then if I increase the U value further, then I get into this insulating state over here, as shown over there. Now I would like to, before I explain further, I would like to go back and make some schematic drawings. The schematic drawing that I'm going to do is a very simple band dispersion. All that I've done is this is one piece and that's the other piece, and think of a system where the charge carrier concentration is such that this part is occupied. So that of course makes it an insulator, right? But mind you, one trick that I built into it is that it's an indirect insulator, indirect gap insulator, not a direct gap. So this is going to be an insulator, and that insulator, its strength, how much the gap is, will of course depend on the Coulomb interaction strength. So if I now, starting from this insulator, slowly decrease the Coulomb interaction strength or increase the W as you like, so U by W, if I go on decreasing, slowly I'll reach a state of a critical value of U by W where these two pieces will begin to overlap with each other. And beyond that critical value, if I decrease the U by W any further, what would happen is, of course, there will be a metal state. And this metal state happens because the electrons from this part would flow into this part. So it's a self-doped metal, where one part of the band structure dopes the other part of the band structure. There's a very important consequence of that, which is that it's a compensated metal. It has exactly equal number of electrons and holes, which has an immediate consequence on the Hall data, right? Of course, we have vacancy in the system, and how do we do that? So if there's a vacancy, I'll move this up and down depending on whether delta N is plus or minus. In effect, what we have in this case essentially minus delta N, because I told you nickel vacancy, which is the hole doping. So hole contribution will lower this, electron contribution will decrease, and hole contribution will increase as I change X concentration, because X determines delta N. And this is what I'm going to do and show the results out of this electronic structure that I've done. But first to tell you that this schematic is exactly what we are looking at, I'm showing you the insulating state again. At 3.5 electron volts, and if you look at this insulator, you can see the gap, and these are the two pieces that you're interested in. There's actually a degeneracy. I'm simplifying it. You can think of the two parabolic things out there and one here. And as I decrease U, the systematic will come closer and closer, and this piece and that piece, they transfer electrons, creating holes and electron pockets. Right? And that's what gives rise to this firm surface, which is completely different from the other one. Okay. Having done that, I can go back to the phase diagram that I've told you about, but here now then I can add in an important thing, that it's a self-dope, and because of that, it's compensated. And it's compensated not just because it's self-dope, but this self-doping is within the nickel D band. Of course, hybridized with, because the other self-doping case that you know about, chromium dioxide, which is a self-doping between the oxygen P and the chromium D. But here is a self-doping, a very unique self-doping where one piece of D band dopes another piece of D band. Okay. Having done that, then one can ask, so what is the consequence of this? I'll do very simple-minded calculation based on this, counting the electron pocket and hole pocket, and see what the consequences are. I'll be very brave and say, let me calculate the Hall constant, let me calculate the conductivity. By this very simple way, where I easily can find out these quantities from my positioning as a function of X. I can also find out these quantities by looking at the curvature of the dispersions. So everything that I need to know is already there in my calculation, and if I do that, for the conductivity I get this. This is the experimental value, and this is actually what we calculate. You can see that the rough increase and similar increase is already there. And it's within the order of magnitude correct. And I'm really ashamed to show you what I'm going to show you next. Please don't hold it against me. If I divide that theory by 3.5, then this is the red points that come about. I don't own up any responsibility for what happens there, right? But it happens. And then I, of course, get excited by that and remember the 3.5, and I go and look at the Hall data. And this is the experiment. And that's a theory. And I said, no, I'm not going to fit. 3.5 was fitting, and I'll not fit. I'll use the same one, 3.5. Because after all, remember, mobility is a product of the conductivity and the Hall constant. So if I have to keep that the same, mobility the same, since I divided by 3.5, I must multiply by 3.5, and I'll do that. And if I do that, I get that set of data as a function of x. Okay. Then one would say, fine, go and look at various spectroscopic data. This is the photoemission density of states, basically. You can see that this one is the antiferromagnetic metal, the red, and this is the non-magnetic metal. And what we essentially see is that there is a shift of the rate from the main peak in the spectrum will shift from high binding energy to lower binding energy, exactly as was seen by Fujimori. There's continuous densities of states right across. It's always metal, but there's a depletion of density of states because of what happens is in the antiferromagnetic metallic state, parts of the Fermi surface drop out, but other parts still remain, and that's why you have a lowering of the intensity. And then we go and look at the optical data. Here, the optical data is a bit more, I have yet another fudge factor, please let me explain to you. But this fudge factor is again something that is well known, is required when you try to do these density functional theories and try to look at the unoccupied densities of states. This is both from X-ray absorption, Brent-Riley isochromatic spectroscopy. What happens is that this is a fundamental problem of any of these ground-state calculation in trying to describe the excited state phenomena. So because it's an excited state phenomena that you're looking at, and what is more complicated here, you will have Coulomb interaction between the electron and the hole. And that would again give rise to contraction. So one knows that one needs to contract the energy scale. So what we have done is calculated exactly as it comes out from the results and then done a contraction of the energy scale. And this is the experimental data, and that's our calculated data with a 30% contraction of the energy scale. We're looking at possibilities of actually avoiding this contraction. We're looking at possible ways. There are 2-3 things that potentially contribute to this contraction that we see here, and we are looking at some of them. For example, Coulomb interaction effect beyond the kind that we are handling may contribute. We have already seen with DMFT that we actually have a contraction more than what we get from LSDA plus U. We are also looking at if it is possible to do some kind of excited state calculations, and so that story is not yet complete, so the jury is still out. So with that, let me come to the concluding part. I'll not go over the entire thing, but let me just summarize saying that the low temperature phase, which is the enigmatic one, is essentially a self-doped, newly compensated antiferromagnetic metal. And with that, let me conclude my talk. Thank you for your attention.
Can you show the band structure again? I just wanted to make sure where the sulfur states really are.
A and K points. Yeah. So these are the A points, the whole states, which are here, the Fermi surface.
No. My question is where is the sulfur? Where are the sulfur bands here?
Okay. The main sulfur bands are below.
Yes.
Are below that. Okay. Let me show. Well, remember the energy scale here, it's 1.5. These are all, if we analyze the data, it shows there's a lot of sulfur admixture, lots of sulfur admixture, enormous amount. But the nearest that I can show you to answer your question is sulfur band is here. And we have been looking at there. Okay?
But when you say it's nickel-nickel self-doping, this whole
these have
also has sulfur character.
These have a lot of sulfur character.
It does.
But these are dominantly nickel, but means a lot of sulfur character. And the other thing is that I did not mention that within what I've presented, we also understand this antiferromagnetic structure that's seen, the AB plane ferromagnetism or antiferromagnetic along the C-axis. That comes essentially from the structural aspect, but okay. I do not know of that experimental data. So specific heat data, I cannot offhand recall. So I really won't be able to answer. But I'll keep that in mind, and if I find it, I'll send you, and if I don't find it, I'll thank you.
Is there an RFSX
ARPAS, in fact, Fujimori and I together we tried. These don't cleave well, so it's very difficult to do ARPAS. At least so far nobody has done ARPAS. I think
Passing the mic.
Since it's a nearly compensated metal, I was interested if you have done any magnetoresistance measurements.
We did some magnetoresistance measurement of this. In fact, for also a different reason, when magnetoresistance was very popular in 93-94, we tried with very high fields also in collaboration with Japanese. The magnetoresistance is weak. It's not very anisotropic. The simple crystal data is available for transport. It's a factor of 3 within each other. If I remember right, along the C-axis is more conducting than along the AB. And the reason for that is also tied up with the magnetic structure. The reason we have ferromagnetic structure in this direction is because what I told you is phase sharing nickel sulfur 6 octahedra, and that defines the angle between nickel sulfur nickel to be 90 degrees. So that's a super exchange ferromagnet. And along this it's an 8th shared, and it's a super exchange of 60 odd degrees, not 180 degrees, but 60 odd degrees again will bring you back to the super exchange, which is antiferromagnetic. And that's the one that gives. So in this direction, it's more strongly coupled than in this direction. So there is some amount of anisotropy.
Can I summarize your picture by saying that because sulfur is so covalent
Because sulfur tends to form very covalent and is very hybridized, I can think of the problem as essentially a small negative charge transfer energies where the antibonding band of sulfur is only partially occupied. Sulfurs do that, right?
No, I do not think you can think of it that way, because